All right, so primarily we'll deal with the Newton's method today. Last time and the class before, we looked at gradient descent in great detail. Newton's is somewhat special, so let's see what we can do with it. But before that, I want to do something. All right, some interesting property we'll deal with first. So definition. We briefly mentioned it, I didn't stress it enough, so let's see. So consider a descent algorithm that starts at x0 or x1 if you like, and updates are x1, x2, xk. Apply an affine transformation to x0, the starting point, to get y0 is equal to some matrix A times x0. All right. And use the same descent algorithm as you did with x0. As you did with x0. So what are the iterates now? The iterates are y1, y2, and so on. If right, for all A, the algorithm or the descent algorithm is called affine invariant. Understand the meaning first, and then we'll see what algorithm is affine invariant, what algorithm is not affine invariant. Algorithm clear, or rather, the definition clear? So give me an example where it is and give me an example where it is not. Again, if the definition is not clear, I'm happy to elaborate. What are we trying to do? We're fixing the starting point. Okay. So starting point is fixed. If you proceed along the algorithm, let's call it script A, you'll get certain iterates x1 through x5. Here, I take a transformation. I multiply it with x, so to produce y0. Now, starting from y0, I apply the same algorithm. I'll get y1 through yk. Does this keep holding is the question. This relationship that I can get from x1 to y1, xk to yk. If it does, then it's called affine invariant. If it does not, so we saw something where this was broken. Because if it was true, then you would not have got any improvement as such. We saw some convergence result which depended on the eigenvalues of the matrix Q. Sorry. Thank you. Both should be, so I've swapped the order. So if you remember, we tried to show the convergence result for the quadratic problem, which was minimize X transpose QX. And the guarantee we got depended on the eigenvalues of Q, which was something like lambda max minus lambda min over lambda max plus lambda min. And then we said, if you do something with the matrix or to the iterates, you could actually improve it. Said something of that guy. If that is possible, will this property hold is a question.
In that case, one thing converges faster than the other.
Right. So exactly.
So then you can't, it's not like the 5 minute.
That's why I wanted to point out. That should come back to you. That the fact that by transforming, I'm doing a better in terms of convergence rate. It cannot be that these two are identical. What is essentially this is saying? That if you give me this, I can go back to that. If you give me this, I can go back to this. So the convergence cannot be faster in one domain compared to that. And if that is happening, that means that algorithm is not a fine invariant. There is room to improve if you were to transform and then begin your algorithm. So what was that algorithm? Which algorithm guarantee, which we prove, to have a convergence rate which was lambda max minus lambda min over lambda max plus lambda min? So steepest descent. So the first thing you should try to prove is that steepest descent is not a fine invariant. Okay, so how does one prove that? Is the definition clear to everybody? Okay. So now try to think, why is gradient descent not a fine invariant? Steepest. So let's try to prove that steepest descent. So you may not realize the power of this, but can somebody say why it is useful to think of algorithms which are fine invariant or not? So if you come up with an algorithm which is a fine invariant, what stops? There is no need to look for the right basis in which to optimize. Do what you want. You'll get the same answer.
There's no need for the right
basis. Essentially, by transforming, what are you choosing? You're choosing the right basis in which to perform your optimization. If your algorithm is affine invariant, it's not going to change. That's the whole point. And that is why it is important to know whether your algorithm is affine invariant or not. Okay, so steepest descent is not affine invariant. How does one claim that? So let's say x0 is your starting point. What am I going to do? x1 will look like x0 minus eta del f of x0. So how should I proceed? And in comparison, what will be ax1, or rather Yeah, I want to compare with and without transformation. What should I do?
If we take y1 y not equal to ax now,
Mm-hmm.
and then y1 will be equal to ax not minus delta error. So gradient error variance.
Mm-hmm. Yeah.
We have to do this.
Yes. And okay, so what are you saying? I start with ax naught minus eta del f ax naught. Okay, what is this equal to? Y1?
Right.
Okay. Now what? Sorry?
So, so we need to prove that y1 is not equal to ax. For some.
Okay.
Right. But if we can prove that function fails, like if ax naught is not equals to a of x naught. I think I have to like basically prove that y1 is not equal to ax1 for some.
So just so that I can follow my notes here.
Sorry, this is by let's just please.
Carry on.
Implication does not hold.
So let me actually flip it around just so that I can am consistent with my notes. Nothing will change, but let's see. This is true. A is invertible, so it won't matter. X0 is equal to AY0. And then all right. So look at A inverse here. That's what this is. So we can just erase this for the moment. Okay. Now tell me what I should do. So X0 is some AY0. And define G of Y to be simply F of A. What is gradient of GY? A transpose F of should be sorry for that. Okay, this much. Okay. Now what should I do to prove that it's not a finite variable? Now this is one line. So my update in X iteration is here. What is my update in Y? Or equivalently, what can you write? AY1 is equal to minus eta
Gradient error.
but that is defined to be G of, so let's write equal to AY0 minus eta del G of y0. Sorry.
Transpose inverse.
But using this, I can also write this as a y0 minus eta a G of y0. Is that correct? No, that's not correct. What can I write this as? This is not correct. What would be correct? What do I want to show? That x1 is not equal to? That's all I want to show. X1 is this quantity. And AY1, I'm trying to compute. Somehow I want to show that this is not true. So what is the appropriate thing here?
If it was equal, then you would have that the gradient of f of x naught would be equal to is equal to gradient of g of y, right? Like, because a y1 is saying is, let's say that x1 is equal to a1. So then x naught minus eta gradient of f of x naught is equal to a y1 minus eta gradient g of y0. So but x naught is equal to y0 we've taken already. So that's the only thing. So then we have that, and eta is the same. So you have that gradient of f of x naught is equal to gradient of g of y.
Mhm.
But gradient of f of x naught is a gradient of a by naught.
Okay.
Gradient of f of a by naught.
Mhm.
F of by naught. This is the gradient of a. Gradient of g of, but like.
Something just plotting gradient of gradient.
Yeah.
That way you will get a y naught is x naught. Eta a transpose f of x naught. And this is not equal to.
That's all right. All this is planted. So you're getting an extra A transpose in the process compared to the iterate of x1.
Sorry, right?
What is the last step which I have not written? It's eta times gradient of gy0. What is gradient of gy0? It's A transpose f of ay. Ay is same as x. Ay by definition is nothing but x. So in the process, what are you end up getting? Ay0 minus eta times A transpose. What do you want back? You want back gradient of f of 0. To compare, make the fair comparison.
Yes, sir. Isn't the gradient g of a is equal to a transpose gradient f of a1?
I know.
So f of x naught should not be an eigenvector of a transpose
What?
value 1.
We don't have to say all that. Because otherwise, if it belongs to whatever you're saying, things will be wrong in a different way. Is this correct? This is not correct, right? When g of y is f of ay, what is gradient of gy? Should be okay. Now, this is what I really wanted. Right? So, what is this quantity correctly? So, suppose I write directly, check this. A transpose del f of x0. Is that correct?
Why is there an extra?
Check if that's correct or not.
No, that's not correct.
Okay, so what should I remove? The gradient of FAY0 is what? This is not correct, right? Quite correct. What is that equal to?
A trans.
Which one? There's some inverse involved here. Okay. What should I add here? A inverse. It transpose of the inverse. Okay. Now what will I get? What do you want me to put here? You can avoid all this trouble. You can directly also write if you want. I don't mind. So what is gradient of f of ay0? That's all you really care about.
So if we replace by, if we replace y1 by a trans a inverse x dot.
Okay, let's just remove all this. What is this equal to? Ay0 minus eta what? In terms of this.
Here, gradient of f of. Let's see.
What happened? Something happened.
First, like we can begin again with this, like we'll do that. I'm very confused a little bit. So let's say that x1 is equal to x0 minus eta f of x0. So that's the first starting point.
That's just on its own. It's happening in the x domain.
So now,
What's happening in the y domain?
so now we want to prove that ay1 is not equal to x1. So first we just begin, so x0 is equal to ay1, we fix it.
Okay.
And now y1 is equal to, if you apply the same algorithm, you would get that y1 is equal to y0, y0 minus eta gradient f of
y.
You get the same root again. Yeah, you're just applying the same algorithm on. I want the gradient is the same percentage, right? So the eta will be different. But it's once. Just apply the same algorithm.
For the moment, let's take the gradient descent. Let's keep it eta itself. Don't worry about choosing the right step size.
Right. So and then ay1 would just be equal to ay0 minus eta a gradient f of y0. Yeah, so actually it's like ay1 is equal to ay0 minus eta times gradient f of y0.
Okay.
But that's not equal to gradient f of a1, which is what is written there.
Okay. So why are we going around and around? Okay.
So, first of all, you have to prove that a y1 equals to x1. First of all, right?
That's precisely what I'm
Yeah,
after.
but we are not doing. If you don't do that, if we just follow the formula that y1 is something that is updating as the previous formula, like y1 equals to a naught minus eta gradient of ax naught. And if we achieve a inverse there, then we can take the inverse this side and we can make it x1.
Okay.
So if we are not getting a inverse there, then that means that the update is not the same as the x1. If we are choosing a y coordinate, this is a new coordinate system.
Why is ay1 equals to ay1 minus the gradient of a1? And we don't know that if that's correct. So that gradient of, it shouldn't be gradient of ay1, it should be a gradient of f1.
Go ahead.
And you are a1
Let's do it. Yeah. What are you saying? ay1 is equal to
a1 minus a times eta of gradient of f1.
a times Eta times gradient of
Is or not even.
y now. Okay, y. Is this equal to this? No. I take it independently. No. Independently. How are you getting this update? What are you doing with this?
Just, I mean, we're doing the same algorithm of y1 and then putting the transformation A on that.
Okay, so you're essentially writing y1 and then multiplying a to it. Why don't you say that? That's much easier to say, right? So let's just write it that way. And is this as well? Okay, so independently iterating over y, we'll get y1 is equal to y0 minus eta del y0 multiplying by a. We get ay1 is equal to ay0 minus eta del f of y0. What is this quantity equal to? That's x0. This quantity is equal to x1. By definition, just imagine for the moment. I would have liked this to be equal to this. Now, what is this? I should say that this is equal to x. What is this quantity compared to this quantity? But this is y0, and y0 is equal to yes, a del f a inverse. Sorry. Now what should I do? Okay, so what will turn out?
Then A inverse transpose.
Okay, supposing A inverse is identity, what remains?
We just get gradient f of.
You remain with f of the g of y1.
Why are you going G to now again? Why are you going back to G? What is the gradient of A inverse x0? It's A inverse times gradient of A inverse x0, which is not equal to, so that extra A inverse is going to create trouble for you. So A inverse cancels. This is not same as this. So the iterates are not going the same way as you would have liked. You would have liked this to be equal to this. Question?
It's x naught is an eigenvector of A inverse
Okay.
with the eigenvalue 1.
If, okay,
Then it will be equal.
then it will be equal. But this has to be true for all A's. This has to be true for all A's by definition, not for some special A's. It could be possible that for some special A's, they might end up being the same.
Basically, A is itself not affine yet.
F is some convex function. That's all. Okay, now come up with an algorithm which is fine invariant, because otherwise you would not have. Yes.
Is that thing correct? Gradient of G1, yes, that thing.
Okay. I deliberately erased it. Now what is the problem? Okay. Okay, now an algorithm. See, sometimes making mistakes in the class helps the students. Making mistakes in me making mistakes, algorithm, that is.
So like regarding the question that he has regarding the steps,
Yeah.
it's not saying then how to.
We're not doing steepest descent. We're actually proving this for gradient descent. If you just simply just picked any for fixed eta, you're just multiplying the gradient. This holds. So any algorithm which just does this is going to be not a fine invariant. If you did eta also specialized, you'll have to work harder. That is a fine invariant. Anything that comes to mind, it should be a fine invariant. Newton's. What's the algorithm I have given you? You're not really looked at any other descent algorithm. Okay, so why is that fine invariant? People remember what Newton was? Or should I write down?
X1 will be equal to X0 minus f of X1 by gradient of.
No. So xk is equal to xk minus eta Hessian xk inverse times the gradient of x. That's it. Okay, so remember, we are doing this x0 is equal to ay0 transformation. Now, what's going to, so what is my yn plus 1 times is equal to yn minus eta del square. So I'll define what g is for a moment. Gy and whole inverse del g of y and del g of y is equal to f of is this correct? This So now I'm going to pre-multiply this with a. So I'll get a times yn plus 1 is equal to ayn minus eta. All of this. Now what can I simplify this as? A transpose something. Hopefully I'm writing it del square a by a whole inverse A transpose AY. Just taking the Hessian and the gradient.
Why?
Sorry?
Why?
Y. Does something simplify here?
You are cancelling out the A inverse and A transfer from both sides.
Okay.
So it will be eta Hessian of FAY inverse
Mm-hmm.
FAY. There will be a tail. Missing a tail.
Where? Okay. What else am I missing? So you're opening this inverse somewhere.
Yes.
What are you writing the inverse as?
So A inverse, the ratio of FAY inverse. A transpose.
This will cancel, this will cancel. What will remain? Just this part. Okay. So this is AYN minus eta del square. Sorry. What is AYN? Is nothing but xn. So you get exactly what your update you started. So AYN. Sorry. Yeah, so if it was true in one step before, it remains true thereafter. That's what it says. So this in between multiplying by the inverse of the Hessian essentially takes care of that. It's not the huge. So this is in general not a descent direction. This algorithm, as long as this is not positive definite, it's actually not a descent direction. But this special structure induces something, which is the affine invariance. Now, what is in the previous thing we said, if you change the way you're running your algorithm, you could change your guarantees. Here, there is no room. Now you do whatever transformation you want on the space, you're not going to get any different answer. So Newton is that way invariant. Shall we move ahead? So now the rest of the lecture today, I want to prove the convergence for Newton, which has a very strange property for strongly convex functions. So the assumptions we are going to make is assumption 1, that del square of x. So this is squiggly, okay. Hopefully you understand now what this means. That means this minus this is what? This is squiggly. Was similarly this minus this. Or you can equate trying to write x transpose del square f of x times x is greater than equal to m for all x, less than equal to capital M for all x. That's all this. This is squiggly. This is equivalent to what? We also call it strongly convex with parameter m, little m. That's what essentially this is. And 2, again, something similar, but now we want Lipschitzness in terms of the second derivative. So del square f of x minus del square f of y is less than equal to the 2 norm. Last time you only demanded in the gradient space. Typically is demanded without the gradient at all. When we say Lipschitz, function of Lipschitz is just f of x minus f of y. Last time we demanded smoothness, which is gradient satisfies the Lipschitz. Now this is something even more. The second derivative is Lipschitz. Now what we are going to prove is somewhat special. So under these assumptions, Newton's algorithm has a two-phase behavior. A, if the gradient at a particular point xk is greater than equal to eta. Let's not call it eta. Let's something else. Call it some eta, for example. Then what are we going to get? We're going to get something like f of xk minus f of xk plus 1 is going to be greater than equal to some gamma. So this is not precise. I'm just trying to explain what we are going to see. What does it mean? All I'm getting is reduction. I'm not getting really the quadratic convergence I had hoped for. We proved something that for the Newton's method, if the iterates are close to the global optimal, then it converges quadratically. We're not seeing that here yet. Reason is the gradient is far enough. Even under these assumptions, if the gradient is far enough from 0, you're going to move slowly. In the phase B, once this becomes small enough, then it starts to suddenly change. So there is some theta. It's not the result I will write is precise, but essentially you should think of there exists some theta for which this two-phase behavior happens. Then essentially L by 2m square is less than equal to L by 2m square gradient of f of xk square. Remark the square here. Then once you cross the threshold of theta in terms of the gradient, then there is something quadratic going on. That the gradient at step xk plus 1 is smaller than square of the gradient time xk. From here, one can derive the convergence result. So this is essentially what we are going to show. So suppose this is true. How do I establish quadratic convergence? Is this clear what we are trying to say? That there exists a theta, that if it is above, then it goes slowly. If it's below theta, then it is quadratic. But quadratic currently is not in terms of convergence, it's only in terms of the gradient. Can you use this to establish quadratic convergence? I claim that is sufficient to claim that. So what's happening in the gradient domain?
One, gradient is will be bounded by theta for the kth iteration. Then also for the subsequent iterations, also the gradient will be bounded by theta.
That's what we've been shown.
Yes.
That needs to be established.
I think x3 plus 1 is x and
Yeah.
instead. So we just prove that x3 plus 1 minus x star. Mounting so that is less than or equal to.
Yeah, but does it give you that? Does it give you that this inequality? So don't try to prove anything. What does it imply? Just tell me loosely. If the gradient is falling in a square manner, what does it imply? If theta was smaller than something, it will be meaningful. If theta is not smaller than something, it's not meaningful. What is that theta for it to be meaningful?
Yes, yes,
1. No, that's not sufficient.
yes, half.
Look at this. It's not
Okay.
independent of
So,
everything.
right, theta should be less than L by 2m square.
Or the opposite.
2m square by yeah.
Okay. Then why is it meaningful?
Then the constant will go
Because the whole thing is less than equal to 1. And then I can think, so as long as theta is less than m square by L or m square by 2L, because half doesn't matter, half is okay. Then I'm actually in business. And what is happening? Then it is falling as, let's say, half. So just pick theta to be L by m square. What is the right hand side? It's at most 1/2 square. So if I do this k times, what am I going to get? 1 by 2 to the power 2k. Right. So this is in the slope domain. But now my functions are also strongly convex. Can I port that to the function also? Okay. Which inequality will it work? See, what do I need? I'm currently showing only that the gradient is falling fast enough by picking theta, supposing theta is smaller than n. This is 1 by 2 or 2k. How do I port it back? What do I really care? I care about f of xk minus about. The guarantee I have is about del of f of xk. You don't actually have to go back all the way. What does it tell you about just this? How much? That f of xk, or rather f of, yeah, let's just do it for general y. F of y is greater than or equal to f of x, and specialize it to x star if you want. With this strong convexity, what do I have? F of x plus something plus something. What is that plus something?
That's the gradient. Yes.
by 2, and this quantity is greater than equal to little m. Right? That's what essentially is strong convexity. How can you use this in addition to this to claim something about this?
So if you put a x star,
Mhm.
and so if we put replace y by x star, x by x star, so x star is the optimal solution.
X star is optimal, yes.
Yeah. So del f star will vanish,
Mhm.
and at the optimal case, the del square f x star, the Hessian, using the
See, if you make it disappear, then how are I going to use this? What
then you can change
the guarantee you're getting is in terms of at xk plus 1.
okay, then you can change the rule.
Okay, change whatever you want.
So if we just do y is x star and x is and x k.
See, there should be some controller. F is convex, strongly convex. So knowing something about the gradient should tell you something about the distance from the optimal.
So right now we're focusing on f of x star minus f of x k. Firstly, using the assumption one, we can bound the del square Hessian of fx star, fxk, and also from the below part, we have a bound of theta on f del of fx star.
Okay. Del of fx star is 0.
Not fx star, del of fxk.
Okay,
I am standing on xk.
fine.
And if we have to bound the fxk minus fx star, right? So we have to take all the rest of the side to the right hand side and the fx star in the left side. And what will get?
Okay, forget about this. Just assume that you're given the function to be convex or strongly convex. And I give you a guarantee that my gradient is falling down as 1 by 2 to the power L. What is your expectation in terms of being close to the x star? Maybe you're getting lost in the equations. There should be some control. It can't be arbitrarily that the fact that gradient is very small, but you're unable to control the distance from your optimizer. That can't happen for a strongly convex or a convex function. For an arbitrary function, I can't say. That's difficult. That's by definition. Okay. Take y hat is equal to x minus 1 by m gradient of x. What can you say in terms of y tilde now? This is true for all y, right? So this is also true for this quantity. What will you get?
If of y tilde my is equals to
Arey yaar.
fx plus the gradient of f square. By m.
X and x will cancel. You get a minus 1 by m
Gradient of x.
square plus m by 2. What is this quantity? X minus 1 by m. This will also cancel. You get a half here. But this is a square. This is a minus. So what do you end up getting? Equal to f of x minus 1 half 1 by m times del fx whole square. But this was, you didn't see this coming. Okay, so now tell me, whatever I've shown earlier, isn't this sufficient? So what is happening? This is converging at a quadratic rate that essentially tells you that f of x minus f of x star is also converging at the same rate. So it's only true for strongly convex functions. So that's why the strongly convex function is very useful. You can estimate the distance from the optimizer. So in other words, what is true for strongly convex functions? That estimating this is sufficient to estimate the gap from the optimizer. Why? Give you the punchline. This holds for all y's, right? So the left hand side, I can essentially try to minimize and say that is P star or like the optimizer. So the optimizer optimal value is at least as much as any point f of x minus 1 by 2m times the gradient square. So if your gradient square is going smaller, the gap is only so much. That's the whole point. This is the gap from the optimal value. That's the point. And that is why strongly convex functions are so useful. This is not true for just purely convex functions. You can't do all this. Okay, so in the limited time I have, let me try to prove what I wanted to prove. What do I want to prove? There exists a theta which is small, theta which is smaller than m square by L, for which this happens, is what I want to prove. And one important detail I was hoping you would ask. I've written Newton's algorithm, but I never specified how to choose the step size. So I was hoping somebody would ask. So step size choice is Army's rule. Last time we showed lots of things with a constant step size. So let's call it proposition. There exists constant theta comma gamma such that if theta, then f of x or k is greater than equal to. So that's the first phrase. So for notational simplicity, I will take the iteration to be x going to x plus. Okay, so just easier that. So this is xk and this is xk plus 1. The next iteration. So what is f of x plus is equal to f of x plus eta is my step size and how much I'm moving. So let's, what did we call it? D, right? Call it D, which is equal to less than equal to f of x plus eta gradient of f of x transpose D plus m times D square by 2 times. This is okay. Just second order Taylor approximation where I'm substituting for the assumption I made earlier that Hessian is less than equal to capital M times identity. Now define this new quantity which is actually of independent interest. I'll tell you what's the name given to it. So define this to be D transpose the Hessian D. But D, remember, let me call it D to be Dn, which is to represent the Newton. So this quantity is actually has some nice name to it. What is the name? Called something. Yeah. Called the Newton decrement. Right. And what is dn? Just to remember, dn is nothing but gradient square f of x whole inverse gradient of x. Just to remember that. That's what your dn is. Okay, so is this greater than equal to m times dn square just by my little m strongly convex function? This is true. Okay. Now what we care about is this equation. I want to control this step and I want to control this step. So lambda square is already controlled by this quantity. What can I write this as?
So, like lambda square is equal to this, and that thing will be less than or equal to that we can take the modulus and the dot product.
Just use this in there.
Oh,
What do you get lambda square also as? Yeah. So then can I replace this somehow? So I want to write lambda square also equal to minus of the gradient times dn. That's just by substitution. Okay. So what is this quantity? This is essentially minus of lambda square, eta, nothing else. And what is this? Dn square is less than equal to lambda square by m. So I can write following everything. Everybody's with me. This term is here, which is minus lambda square. This thing is lambda square by m. So I get f of x plus less than equal to f of x minus eta lambda square of x and plus capital M by 2m eta square lambda square. So now, anybody remember what the army rule was? Don't forget it that easily. It's a very important thing. Let x be greater than 0, beta belongs to 0, 1, sigma belongs to 0, 1. You start with the step size alpha equal to s and then try alpha equal to beta s, beta square s, and so on until the largest alpha for which the decrease is bounded, which is f of xk minus f of xk plus alpha dk is greater than equal to minus sigma alpha, the gradient, times, that's your armure. Okay, so if suppose here I pick eta is equal to little m over capital M, can I satisfy this condition is the first question. See, this is x and this is x plus. Right? That's the change I'm making. So if I choose the step size equal to little m by capital M, is this inequality satisfied? Why?
Eta is also less than 1.
Eta is less than 1, yes. That is not sufficient. We plant eta equal to little m by capital M. What happens to this equation?
In small n by 2m.
So f of x minus
Small n by 2 capital M.
lambda square x. This will essentially cancel off, right? What will you get? You'll get again another m by capital M 1 by 2 times lambda square x. And this is actually equality f of x minus 1/2 by capital M lambda square x. That's what you will get. Now, why does it satisfy this? What is the definition of lambda square x? This much. So what am I getting? 1/2. So I could have chosen that sigma to be 1/2. Alpha is nothing but this little m by capital M. So I actually get to satisfy this. So this choice satisfies Armijo. Since del square x is nothing but gradient f of x times t. No? Yes? Or minus? Minus here, I think. Yeah, minus. So in the worst case, I will go to 1 less than that. If certain choice follows Armijo, because I'm starting with some s, I may not exactly stop at that, but I might stop at, in the worst case, beta times little m of them, because I'm looking at the smallest choice. So therefore, at eta is equal to beta times m by m, the Armijo rule will terminate. For sure. It could terminate exactly at little m by m also. That's also fine. See, beta is less than 1. So I might stop there or slightly smaller. So that this implies that f of x plus minus f of x is less than equal to minus, it's alpha now. Eta lambda square x, which is less than equal to minus alpha beta m over m lambda square x, which is less than equal to minus alpha beta m over m gradient of x over capital M. I'm just writing these things without thinking through because we have. Why is this true? Just by definition of lambda square. Nothing interesting going on. Okay, so what have we now? What have I shown? Essentially, that fx plus minus fx is less than equal to this quantity. What do I want to show?
fx minus fx plus is greater than or equal to.
No, that is just a rehashing of it. What did I want to show? What was the proposition I started with?
Constant.
Some constant. So what is that constant which will work for me?
Yes, gradient of f of x.
So if I put a limit on this, I will get a constant. So if this is greater than some eta, see, that's the thing I want, right? That if this is greater than theta, then this is greater than nu. So put this quantity as theta, all of this as your bound, which is exactly what I want. So fixing del fx to be greater than equal to theta, we get the result. We've done really nothing so far because that's the weak result. All it said was that if the gradient is larger than something, it slowly converges. The more interesting part is next. And amazingly, it's raining right now. It's thunder and rain in November of 8th.
It's so hot so far and suddenly.
At least the pollution will come down. It won't change the temperature much. All right, any questions on this? You're mostly doing elementary steps and recalling what you've built so far. Nothing really new, spectacular is happening. This is one quantity you might want to remember, Newton decrement. This also happens to have a fine invariance. You can go home and check. It doesn't matter what you're doing. Essentially, this quantity, the fine invariance, actually makes the Newton. You can vice versa, you can think about if one is invariant, the other better be invariant. But this has some other nice properties also, this quantity. All right, so shall we go to the final thing? Now, the more important, again, proposition, if del of fx is less than theta, then the Armyho's rule, it's also interesting, selects theta equal to 1. Step size is 1 and L by 2m square del fx plus is less than equal to L by 2m square del fx. Okay, how should we prove this? We've seen that this is sufficient for quadratic convergence. So all we are proving is that the gradient is decreasing fast enough. What would be sufficient to do something like this?
So you use the Convex plus is less than or equal to Convex plus. Yeah. And then we evaluate it like the gradient data Convex plus.
Will it give you anything? So assume for the moment that eta is 1. Okay. Assume for the moment. That remains to be shown. Suppose eta is 1 and gradient of f of x is less than theta. What are you trying to show by doing this? Don't worry about actually proving it. What does it even mean? That the gradient in each step is decreasing quadratically. That's what is really being shown. So if you look at the trajectory of the gradient in each step, what is that happen? We've been writing it as xk plus 1 is equal to xk minus eta times gradient. But gradient itself, can you write it as gradient at xk plus 1 in terms of something something? Let's try to prove, assuming this is true. So let eta equal to 1 for the moment. We'll also prove that this happens to be true. Is this true for my algorithm? Dk was nothing but minus of this inverse times del f of x. So I can always write this. What was dk for Newton or dn? This quantity is inverse multiplied by this. So I'm just moving the inverse over here. All right. And now we'll try to understand the iteration of the gradient itself. How is the gradient changing? So now, what is gradient of x plus? I'm going to add and subtract del f of x to it. So del plus or minus del fx and plus del fx substituted by this quantity. Everybody is okay with that? I'm adding, subtracting gradient, and I'm just replacing gradient equal to this one. Okay, now stare at it. This inequality is nothing but a connection between this, which is on the left hand side, and on the right hand side, there is a decay, but rest of them are just gradients. So if you wanted to prove something like this, what would you have done? Sorry? Triangle inequality. Will it give you square? We did this trick last time also, if you remember. We wrote something, some differences, and then suddenly we wrote an integral.
One integrate for the first.
Yeah, for the last one, I can throw in for free because 0 to 1, it doesn't really matter. The same trick, if I throw in, what is going to be?
So you can use the first, second condition in the.
I don't have to go all the way back.
So
How can I write this as an integral? First of all, just think of that.
integral of. Integral like so 0 to 1.
Hmm?
Integral
Sorry?
Excellent.
There is already a gradient, so I'll take another gradient. So del square f of x plus, or rather, I just want to write in the particular form. So I'll write x plus p times x plus minus x, or this minus del square f of x, sorry, dk, and by dt. And this can even make it less than equal. Everybody is okay with that? Something is wrong there. Should multiply what? Okay.
One
It should also be a that transpose x plus minus.
Here should be
After
after what should I write here?
x plus minus.
Sorry, I can't follow you.
That transpose x plus minus.
But you want to multiply another thing. Why? Just look at the integral of this quantity. Doesn't it look like this quantity? We did this also last time. I don't think there is another requirement here. But now question is this dk. What should dk multiply? Only the last term, right? Not this guy. This guy has nothing to do with dk. So I should put it over here. Okay, now what should I do? We did the same thing last time also.
Yeah, we can.
Throw in Cauchy-Schwarz. What else can you do, right? So what will that give you? See, there was a technical condition given to you ahead of time. We have not used it so far. So pay attention to this. We have been given this, that it is Lipschitz in the Hessian domain. So we're getting closer and closer to using that, because what does it look like? Difference of Hessians. But something I have to get rid of. So if it is Hessian minus Hessian 2 norm times dk's 2 norm, then I can do that kind of thing. How do I do that? I'm almost out of time. So you can actually appeal to your fundamental theorem of calculus and move this inside. Okay. So if this is correct, then what can I do? Then I can just simply less than equal to the Cauchy-Schwarz will be, I can throw away the integral. I can essentially also move the integral outside. Del square f of x plus t dk minus del square f of xk dt, sorry, not dt. Sorry. Now I can apply the condition I have for myself. What is that? So this will be again less than equal to L times. So T times dk right? Okay. Now what? What did I want and what where I am? I want this to be true, right? Am I done or I need to do something more? Second to third, I've done nothing. I've just taken Cauchy-Schwarz. Here, fundamental theorem of calculus should get you here. Dk is not the step size, dk is the direction. Step size is 1. This is Cauchy-Schwarz. This is my technical condition. Gets me so far. Now compare this. Am I done or do I need to do something more? Why? So t will essentially disappear at 0 to 1 integral. Some half will show up. Half is not very important. It's important in the square, but what is the definition of dk? This is dk 2 norm square essentially. This is at most L by 2 dk 2 norm square. What is this dk definition? Nothing but this. And what did we assume that? This was less than equal to theta. So what is this equal to? L by 2 times. Sorry. This is del square f of x inverse del fx. Square? What is this quantity after the square?
condition also the first condition, right?
Which condition?
So you have chosen theta.
Yeah.
In the first case, in the first time, the theta could be if they are far apart, then the theta should be L by M square.
Hmm.
We can replace that here.
Okay, don't worry. What can I bound this by? If del square f of x was defined to be what? To be greater than equal to little m by 2. Sorry, little m. The strong convexity. What did strong convexity tell us? That del square f of x is this squiggly mi and little mi. What can you say about this quantity? It's a something product times something square. It is at most how much? Individual squares. And how much is that individual square really?
1 by M.
1 by m. So 1 by m square. And what will remain? This quantity exactly. So that's where you're getting m square. So
You also
L not disappear. L will be.
no, you have you got you gave a L square.
I don't want L square because this quantity already has L here.
Okay, fine.
All I want is one extra or two extra. Yeah. So I'll get less than equal to L by m square times what I want. And that's the proof. I will put the notes so that you can also find that y eta is equal to 1 is automatically chosen.
Why do you use that as less than theta?
Sorry,
The gradient is, the modulus of the gradient is less than theta.
less than theta. So that is needed for this. That's required for showing that the Armio's rule will pick up eta equal to 1. I'm well out of time. So I'll keep this notes on. Not from the